Geothermal power is power generated by geothermal energy. Technologies in use include dry steam power stations, flash steam power stations, and binary cycle power stations. Geothermal electricity generation is currently used in 24 countries, while geothermal heating is in use in 70 countries. As of 2015, worldwide geothermal power capacity amounts to 12.8 gigawatts, of which 28% of 3,548 megawatts are installed in the United States. International markets grew at an average annual rate of 5% over the last 3 years, and global geothermal power capacity is expected to reach 14.5 to 17.6 gigawatts by 2020. Based on current geologic knowledge and technology, the Geothermal Energy Association estimates that only 6.5% of total global potential has been tapped so far, while the IPCC reported geothermal power potential to be in the range of 35 gigawatts to 2 terawatts. Countries generating more than 15% of their electricity from geothermal sources include El Salvador, Kenya, the Philippines, Iceland, and Costa Rica. Geothermal power is considered to be a sustainable, renewable source of energy because the heat extraction is small compared with the Earth's heat content. The greenhouse gas emissions of geothermal electric stations are on average 45 grams of carbon dioxide per kilowatt-hour of electricity, or less than 5% of that of conventional coal-fired plants. History and development. In the 20th century, demand for electricity led to the consideration of geothermal power as a generating source. Prince Piero Ginori Conti tested the first geothermal power generator on the 4th of July 1904 in Larderello, Italy. It successfully lit 4 light bulbs. Later, in 1911, the world's first commercial geothermal power station was built there. Experimental generators were built in Beppu, Japan, and the Guizes, California in the 1920s. But Italy was the world's only industrial producer of geothermal electricity until 1958. In 1958, New Zealand became the second major industrial producer of geothermal electricity when its Wairākei E station was commissioned. Wairākei E was the first station to use flash steam technology. In 1960, Pacific Gas and Electric began operation of the first successful geothermal electric power station in the United States at the Guizes in California. The original turbine lasted for more than 30 years and produced 11 megawatts net power. The binary cycle power station was first demonstrated in 1967 in Russia and later introduced to the USA in 1981. Following the 1970s energy crisis and significant changes in regulatory policies, this technology allows the use of much lower temperature resources than were previously recoverable. In 2006, a binary cycle station in Channahawk Springs, Alaska, came online, producing electricity from a record-low fluid temperature of 57 degrees Celsius. Geothermal electric stations have until recently been built exclusively where high-temperature geothermal resources are available near the surface. The development of binary cycle power plants and improvements in drilling and extraction technology may enable enhanced geothermal systems over a much greater geographical range. Demonstration projects are operational in Landau-Pfalz, Germany, and Sault-Sous-Forts, France, while an earlier effort in Basel, Switzerland was shut down after it triggered earthquakes. Other demonstration projects are under construction in Australia, the United Kingdom, and the United States of America. The thermal efficiency of geothermal electric stations is low, around 7 to 10%, because geothermal fluids are at a low temperature compared with steam from boilers. By the laws of thermodynamics, this low temperature limits the efficiency of heat engines in extracting useful energy during the generation of electricity. Exhaust heat is wasted, unless it can be used directly and locally, for example in greenhouses, timber mills, and district heating. The efficiency of the system does not affect operational costs as it would for a coal or other fossil fuel plant, but it does factor into the viability of the station. In order to produce more energy than the pumps consume, electricity generation requires high-temperature geothermal fields and specialized heat cycles, because geothermal power does not rely on variable sources of energy, unlike, for example, wind or solar. Its capacity factor can be quite large, up to 96% has been demonstrated. However, the global average capacity factor was 74.5% in 2008, according to the IPCC. Power station types. Geothermal power stations are similar to other steam turbine thermal power stations. Heat from a fuel source is used to heat water or another working fluid. The working fluid is then used to turn a turbine of a generator, thereby producing electricity. The fluid is then cooled and returned to the heat source. Dry steam power stations. Dry steam stations are the simplest and oldest design. They directly use geothermal steam of 150 degrees Celsius or greater to turn turbines. Flash steam power stations. Flash steam stations pull deep, high-pressure hot water into lower-pressure tanks and use the resulting flashed steam to drive turbines. They require fluid temperatures of at least 180 degrees Celsius, usually more. This is the most common type of station in operation today. Flash steam plants use geothermal reservoirs of water with temperatures greater than 360 degrees Fahrenheit. The hot water flows up through wells in the ground under its own pressure. As it flows upward, the pressure decreases and some of the hot water boils into steam. The steam is then separated from the water and used to power a turbine, generator. Any leftover water and condensed steam may be injected back into the reservoir, making this a potentially sustainable resource. At the geysers in California, 20 years of power production had depleted the groundwater and operations were substantially reduced. To restore some of the former capacity, water injection was developed. Binary cycle power stations. Binary cycle power stations are the most recent development, and can accept fluid temperatures as low as 57 degrees Celsius. The moderately hot geothermal water is passed by a secondary fluid with a much lower boiling point than water. This causes the secondary fluid to flash vaporize, which then drives the turbines. This is the most common type of geothermal electricity station being constructed today. Both organic Rankine and Kalina cycles are used. The thermal efficiency of this type station is typically about 10 to 13%. Worldwide production. The International Geothermal Association has reported that 10,715 megawatts of geothermal power in 24 countries is online, which is expected to generate 67,246 gigawatt-hours of electricity in 2010. This represents a 20% increase in geothermal power online capacity since 2005. IGA projected this would grow to 18,500 megawatts by 2015. Due to the large number of projects that were under consideration, are often in areas previously assumed to have little exploitable resource. In 2010, The United States led the world in geothermal electricity production with 3,086 megawatts of installed capacity from 77 power stations. The largest group of geothermal power plants in the world is located at the Geysers, a geothermal field in California. The Philippines follows the U.S. as the second highest producer of geothermal power in the world, with 1,904 megawatts of capacity online. Geothermal power makes up approximately 27% of the country's electricity generation. Al Gore said in the Climate Project Asia-Pacific Summit that Indonesia could become a superpower country in electricity production from geothermal energy. India has announced a plan to develop the country's first geothermal power facility in Chhattisgarh. Canada is the only major country on the Pacific Ring of Fire which has not yet developed geothermal power. The region of greatest potential is the Canadian Cordillera, stretching from British Columbia to the Yukon, where estimates of generating output have ranged from 1,550 megawatts to 5,000 megawatts. Utility-grade stations. The largest group of geothermal power plants in the world is located at the Geysers, a geothermal field in California, United States. As of 2004, 5 countries generate more than 15% of their electricity from geothermal sources. Geothermal electricity is generated in the 24 countries listed in the table below. During 2005, contracts were placed for an additional 500 megawatts of electrical capacity in the United States, while there were also stations under construction in 11 other countries. Enhanced geothermal systems that are several kilometers in depth are operational in France and Germany and are being developed or evaluated in at least 4 other countries. Environmental impact. Fluids drawn from the deep earth carry a mixture of gases, notably carbon dioxide (CO2), hydrogen sulfide (H2S), methane (CH4), ammonia (NH3), and radon. These pollutants contribute to global warming, acid rain, radiation and noxious smells if released. Existing geothermal electric stations that fall within the 50th percentile of all total life cycle emissions studies reviewed by the IPCC produce on average 45 kilograms of CO2 equivalent emissions per megawatt-hour of generated electricity. Kilogram CO2 EQMWH. For comparison, a coal-fired power plant emits 1,001 kilograms of CO2 per megawatt-hour when not coupled with carbon capture and storage. Stations that experience high levels of acids and volatile chemicals are usually equipped with emission control systems to reduce the exhaust. Geothermal stations could theoretically inject these gases back into the earth as a form of carbon capture and storage. In addition to dissolved gases, hot water from geothermal sources may hold in solution trace amounts of toxic chemicals, such as mercury, arsenic, boron, antimony, and salt. These chemicals come out of solution as the water cools and can cause environmental damage if released. The modern practice of injecting geothermal fluids back into the earth to stimulate production has the side benefit of reducing this environmental risk. Station construction can adversely affect land stability. Subsidence has occurred in the Wairakei field in New Zealand. Enhanced geothermal systems can trigger earthquakes due to water injection. The project in Basel, Switzerland was suspended because more than 10,000 seismic events measuring up to 3.4 on the Richter scale occurred over the first 6 days of water injection. The risk of geothermal drilling leading to uplift has been experienced in southern Breisgau. Geothermal has minimal land and freshwater requirements. Geothermal stations use 404 square meters per GWH versus 3,632 and 1,335 square meters for coal facilities and wind farms respectively. They use 20 liters of freshwater per MWH versus over 1,000 liters per MWH for nuclear, coal, or oil. Geothermal power stations can also disrupt the natural cycles of geysers. For example, the Bay of War, Nevada geysers, which were uncapped geothermal wells, stopped erupting due to the development of the dual flash station. Economics. Geothermal power requires no fuel, it is therefore immune to fuel cost fluctuations. However, capital costs tend to be high. Drilling accounts for over half the costs, and exploration of deep resources entails significant risks. A typical well doublet in Nevada can support 4.5 megawatts of electricity generation and costs about $10 million to drill, with a 20% failure rate. In total, electrical station construction and well drilling costs about €2–5 million per MW of electrical capacity, while the levelized energy cost is 0.04–10 cents per kWh. Enhanced geothermal systems tend to be on the high side of these ranges, with capital costs above $4 million per MW and levelized costs above $0.054 per kWh in 2007. Geothermal power is highly scalable. A small power station can supply a rural village, though initial capital costs can be high. The most developed geothermal field is the geysers in California. In 2008, this field supported 15 stations, all owned by Calpine, with a total generating capacity of 725 megawatts.